I'm happy to be here today to talk about TraceCompare, a new tool that can be used to compare different groups of executions of the same task. So performance is a critical requirement for many applications. Unfortunately, many factors can affect this performance. For example, performance can change when there's an update to a program, a library, or the operating system. It can change when there is interaction between different tasks, in presence of a programming error, when the system load changes, etc. Developers don't always know all components of the systems that they develop very well. That means that they are likely to encounter performance variations that have a cause that is hidden in a component that they don't know very well. How can they diagnose such performance problems? Well, they can use tracing. A tracer will record events that occur in all components of a system during its execution. By analyzing the recorded trace in a tool such as TraceCompare, a developer will be able to see the time required to execute about any operation. The developer will also be able to see what operations occurred simultaneously. All that information is very helpful to correctly understand a performance problem. But it can be very tedious to try to understand a performance problem by zooming and scrolling in a trace viewer. In this project, we are interested in performance variations. That means cases where the time of an execution is sometimes correct and sometimes unsatisfactory. We make the hypothesis that in such cases, it would be possible to use an algorithm that automatically highlights the differences between the fast and the slow executions so that we have less data to analyze manually. More formally, we ask ourselves the following research question: can we facilitate the diagnosis of performance variations with an algorithm that automatically identifies differences between two groups of execution traces? The presentation will start with an overview of relevant existing work. After that, I will present TraceCompare, my solution to compare different executions. I will show you 4 case studies that prove that TraceCompare can be used to solve real performance problems. And finally, I will discuss the overhead of the tool. A trace usually contains a lot of events that belong to different task executions that occurred in series or in parallel. If we want to be able to compare these task executions between themselves, we need to be able to tell which events of the trace belong to which task execution. This is not an easy thing to do in a parallel system where each task execution requires collaboration between multiple parallel components. Fortunately, one of my colleagues at Polytechnique Montreal, Francois, developed an algorithm, a critical path approximation algorithm. This algorithm is able to build a graph of dependencies between threads using only events from the Linux kernel. Then, by traversing this graph, it can compute the critical path of any task execution. TraceCompare, my solution to compare task executions, relies on this algorithm to compute the critical path of the compared executions. Then, when we have the critical path of an execution, it is easy to retrieve all the events that belong to it from a trace. Because the algorithm relies only on kernel events to build a graph of dependencies between tasks, it works perfectly with applications that are not instrumented. At Google, there's a tool called Dapper that can also compute the critical path of task executions, but it requires custom instrumentation in all communication libraries, so it is less adapted to heterogeneous environment than the solution developed at Polytechnique. Comparison of different task executions has already been used in some performance analysis tools. First, the frames mode of the Chrome developer tools shows the time required to refresh a web page using a bar chart. The height of each bar indicates the time required to generate a frame, and the colors within each frame indicate in which states time was spent. On this example, we clearly see that 2 frames took much more time than the others to be generated, And because yellow is associated with the execution of JavaScript code, we know that we need to go look into the JavaScript code of the web page to understand this variation. Second, differential flame graph. Flame graph is a tool that we can use to visualize a CPU profile. A differential flame graph can be used to compare two CPU profiles. We first generate a normal flame graph from one of the two CPU profiles, and then we use different color shades to highlight the differences between the two compared profiles. Third, spectroscope is a tool that can generate graphs to represent the communications that occurred during task executions. The tool can then cluster similar graphs, and the authors of this tool recommend to compare the distribution of the task executions between the different clusters before and after any important change to a system. On this example, we can see that after a change, a much larger proportion of the executions required communication with a database. Finally, TraceDiff is a tool used to compare two function call traces. Corresponding function calls between the two compared traces are connected with edge bundles so that a user can easily identify calls that had a different duration or that were made in a different order between the two compared traces. With the exception of spectroscope, none of these tools is really adapted to compare task executions that require collaboration between multiple parallel components. Also, differential flame graphs and TraceDiff are limited to the comparison of two task executions at a time, so they cannot really be used to identify general trends in the system. And finally, the frames mode of Chrome and spectroscope don't provide a fine granularity, so when we use these tools to find a problem, we still have a lot of work to do to find the code that should be fixed. I will now talk about TraceCompare, my solution to compare different task executions. First, before comparing traces, we need to record these traces. A lot of problems that affect parallel systems can be diagnosed using only events from the kernel. But to use TraceCompare, we also need to record a call stack history for each user space thread. This allows the tool to make meaningful comparisons. The events of the kernel are quite generic, so if we have a call stack for each of these events, we can make sure that the comparisons that we make between events from different task executions are really valid. How can we record a call stack history for user space threads? Well, generating an event for each function call is not a really good solution because it slows down applications a lot. Sampling the stack of threads running on the CPU is not a perfect solution either because we could miss the call stacks associated with long off CPU waits. We could solve that by also recording a call stack for each schedule switch event, but it turns out that schedule switch events can occur quite frequently, and recording a call stack for each of them can slow down applications too much. So my solution was to create two new events. The CPU stack event is generated periodically when a thread is running on the CPU. This is very similar to how a profiler works, except that we have a timestamp for each call stack that we capture, so we can build an history. Now, what do we do for off-CPU latency? We have a second event, syscall stack, that is generated at the end of long system calls. A kernel module is responsible to record a call stack in a hash table at each system call entry, and then when the system call exits, we can compute its duration, and if it is above a predefined threshold, we generate an event with the call stack of the thread that made the system call. During our experimentations, we found that using a 100 microseconds threshold provided a good compromise between the completeness of the captured call stack history and a low overhead on the observed applications. The overhead is very lower than if we had captured a call stack for each system call or for each schedule switch. In addition to these two call stack events, in order to use TraceCompare, we need to record kernel events existing kernel events that are used mainly to compute the critical path of the task executions that we will compare. Once we have recorded one or multiple traces, we need to extract information about the task executions that they contain so that we can compare them between themselves. We created a new data structure called enhanced calling context tree that can represent the performance characteristics of task executions. We use that data structure as an input to our comparison algorithm. On this slide, on the left, we have a simple sequence of events, and on the right, we have the expected enhanced calling context tree for this sequence of events. It's very simple. Each node corresponds to a function call. They are annotated with the time spent in the function during the task execution for which we generate the tree, and the edges indicate which function called which other function. Now I added a few more events that occur on the second thread. The first thread spends time waiting for the second thread while these events occur. This behavior is also correctly represented in the enhanced calling context tree. We built a tree from the events that occurred on the second thread, and we merged it with the tree of the first thread. Also, on the second thread, there is time that is spent waiting for the disk. This is not an actual function call, but the latency is correctly represented in the tree with the node D that we see at the bottom of the slide right here. So in summary, this enhanced calling context tree can represent any type of latency that can occur during a task execution. It can be CPU usage, disk or network, wait, dependencies between threads, etc. Also, for each latency, we have the full context. We don't simply have the call stack of the thread that directly caused the latency. We have the call stack for each thread on the chain of dependencies that led to the latency. So here, the first thread spent time waiting for the second thread that spent time waiting for the disk, so we can see the full context in the tree. I don't have enough time to give you all the details of the algorithm that we use to transform the raw events of the trace into a collection of enhanced calling context tree, but it is important to note that while we read the trace, we build something called a state history tree. Our state history tree contains the history of the status and call stack for each thread that is in the trace. So when we encounter an event that indicates the end of a task execution, we can easily query the state history tree to get all the information that we need to build its enhanced calling context tree. Next, once we have recorded one or multiple traces and that we have built enhanced calling context trees for all the task executions that they contain, we want to compare these task executions between themselves. We created a web UI for that, and the top of the web UI shows something called the filters. They are illustrated on this slide. So each column corresponds to a group of task executions, and each row corresponds to a metric. That means that each histogram that you see shows the distribution of a metric within a group of execution. The user can select a region on any of these histograms, and when the user does that, the other histograms are immediately updated to show the distribution of the metric only for the executions that correspond to all the filters that were defined. On this example, we see that in group A, the user selected the executions with a short total time, and in group B, the user selected the execution with a long total time. We see that the running time is the time spent on the CPU by the executions, and we can see that for fast and slow executions, there was always almost the same amount of time spent on the CPU. The two histograms are almost identical. But if we look at the metric number of bytes read from the disk, we clearly see that all the fast executions read 0 bytes from the disk, while the slower one read multiple bytes from the disk. So just by looking at the filters, we can get a general understanding of a performance variation. But if we want to get more details, we can look at the enhanced differential flame graph. This is very similar to the differential flame graph that I showed at the beginning of the presentation, but with two differences. First, our differential flame graph is not generated from two CPU profiles, but from two enhanced calling context trees. That means that they show any type of latency that can happen during a task execution. So CPU consumption, disk or network weight, etc. Also, there is the full context, full distributed context for each latency. Another difference between the normal differential flame graphs and ours is that we don't compare two executions, but two groups of executions. That means that we can compute a standard deviation for each metric within each group and add colors on the differential flame graph only when differences are statistically significant. TraceCompare has already been used to detect, diagnose, and fix real performance problems in both open source and enterprise applications. So I will present you 4 of these successes. The 2 first case studies were made with MongoDB. I ran performance tests on the database, and then I used TraceCompare to compare the executions of queries that occur during these performance tests. The first performance variation that I found was due to a mutex that was held for no reason during a long operation in a journalization thread. So we will look at that in TraceCompare. At the top, I selected the duration metrics that correspond to the total time spent, the total time of the query executions. We can see that most executions took less than 20 milliseconds. But if we look closely, we can see a few outliers that took up to 120 milliseconds. So on the left group, I will select the fast executions, and on the right group, I select the slow ones. If I had used a tool that only provides global metrics, such as the average time of the executions over time, the slow executions could have been completely hidden. But now I have a tool that keeps metrics for each individual execution, so I can look at the slow executions more closely. The differential flame graph, everything that you see in red on this corresponds to extra latency that occurred during the slow executions compared to the fast ones. At the bottom, what we see is the call stack of a client application that uses MongoDB. TraceCompare identifies a dependency between threads that we see right here. So the call stack of the thread in MongoDB that was responsible to process the queries has been merged with the one of the client application. So you have the code of the client application, then the code of MongoDB. And again, another dependency has been identified within MongoDB, a mutex dependency. So the thread responsible to process the queries had to wait for a journalization thread. And that journalization thread made an fdatasync system call that took a very long time. When I saw that for the first time, I decided to go look into the code of that journalization thread, and what I found was very interesting. There was absolutely no reason for that journalization thread to hold a mutex during that long operation. So I was able to make a patch that simply released the mutex earlier, and that fixed the problems. I had absolutely no prior knowledge of the source code of MongoDB to do that. Just by the information provided in this tool, I was able to understand the problem and fix it. And when I contacted developers of MongoDB, I got the confirmation that the fix was indeed correct. The next problem was due to the use of sleep as a way to synchronize threads. It's not a good practice to do that, and in MongoDB, the result was that sometimes there was starvation, and a thread responsible to process queries. The queries were supposed to take about 20 milliseconds usually, but when they were not able to acquire a resource because of the use of this synchronization mechanism, it could take many seconds. So the fix was simply to use a proper synchronization method. The two next case studies were made on applications that reproduce problems that I found in enterprise during enterprise visits. The first one was in a real-time application. In that application, there was a real-time task that was supposed to be executed at regular intervals. Unfortunately, sometimes the task missed its deadline. So we can look at this in TraceCompare. Okay. Here I selected three metrics on which to apply filters. The top one is the total duration of the executions. The second one is the time spent on the CPU. And the last one is the preemption time. There is two modes in the duration metric. So I will select in the left group the fast executions and on the right group the slow ones. We see that both groups spend about the same time on the CPU. So the problem is not due to CPU usage. But all the fast executions have 0 preemption time, while the slow ones have 2 milliseconds of preemption time. So we can guess that the problem is due to preemption. We can look at the flame graph. Again, here, everything that is red corresponds to extra latency that occurs during the slow executions. And there's a frame here, wait CPU, that indicates a preemption. So what we see in red here is the call stack of a thread that preempted our real-time task. When I showed that to the developers of the real-time application, they told me that there was absolutely no reason for that code to be able to preempt that one because it had a lower priority. But when we went into the code and we looked at how a priority was assigned, we found that high priority was assigned to that code, and it was a mistake to do that. So the fix was simply to assign a correct priority to that thread. Finally, the last use case was in a web application that had to make a disk request to fulfill the incoming request that it received. And TraceCompare was able to identify that another process was using the disk at the same time. And TraceCompare knew that the web application had to use the disk and another application used it at the same time. So it identified the dependency and it provided the call stack of that other process. So fixing the problem was easier once we knew what other process was using the disk at the same time as us. Now I will discuss the performance overhead of TraceCompare. It is very important for a performance analysis tool to have a low overhead. Otherwise, the behavior of the applications that we observe will be modified, and the data that we will get won't be really valid. Also, we have seen that some performance variations occur very infrequently, and they can occur only under some specific conditions. So if we have a tool that has a low overhead, we can run it in production and be sure to be able to capture any kind of problem. The overhead of recording the events required by TraceCompare using LTTNG depends on the kind of application. The first test that we made was with an application called Prime that computes prime number. It has a single thread, it makes no system call, and the overhead is 0.2%. It's the lower that we can get. And it's mostly due to the call stack sampling. We made another test with Find that has a single thread but makes a lot of system call and spends a lot of time waiting for the disk. The overhead was 5%. And finally, the last test was with MongoDB. MongoDB has a lot of threads. It makes a lot of system call. There is a lot of synchronization between threads. And that's the application with which we got the highest overhead at 9%. There is other tracers than LTTNG. For example, we can use dtrace on Mac or ETW on Windows. So we wanted to compare the overhead of recording our call stack events and kernel events with Linux, with LTTNG on Linux, and these solutions. For the Prime application that uses a single thread, no system call, the overhead is similar for all tracers. But with MongoDB, parallel applications, LTTNG has the best performance, the lower overhead at 8% compared to 24% with dtrace and ETW. So LTTNG was built from the beginning to scale very well with applications that have a lot of thread, and we see it very clearly on this slide. So in summary, I showed you a way to record a call stack history with a low overhead with the CPU stack and syscall stack events. I also presented a new data structure called enhanced calling context tree that can represent any kind of latency that can occur during a task execution along with the full distributed context. And finally, I presented a user interface that can be used to compare task executions using filters and flame graphs. Our solution has been used to solve real performance problems in both open source and enterprise applications. So it's a good solution. What could we do in the future? Well, our critical path algorithm that we use to identify dependencies between threads works well to identify dependencies due to mutexes or network dependencies, but we could improve it to support more kind of dependencies. For example, we could identify preemption across virtual machines running on the same physical machine, or we could include the work done on GPUs. Also, the comparison works very well when you compare executions that come from the same binaries or from binaries that have small changes, but it would be nice to use static analysis, yes, to be able to make the comparison even after a major code refactoring. So thank you very much. Do you have any questions?
So have you considered using your technique, your comparing technique on traces which are CPU bound, so they're not waiting for something, but it's just CPU time?
Sorry?
So have you considered using your comparing technique on performance situations where it's fully CPU bound and it's not latencies, like wait latencies?
Yes, I have made it. The tree that we use represent when there's a function call, we have a node for the time spent on the CPU. So CPU or on CPU or off CPU latency, the comparison works well with both cases. It says that the comparison doesn't change, it's only how we generate the tree, and the tree can be generated to represent both on CPU and off CPU latency.
Anyone else? How did you decide where to start the diff? Was it just an operation that you were generally interested in, or?
Yes. With this tool, I compare different executions of the same task. So we have to we need a way to identify the beginning and the end of the execution. For example, in MongoDB, I added a user space event at the beginning of queries and at the end of queries. So that's how I select the execution, and then the algorithm automatically identifies all the dependencies between threads, but I need a starting and end point on one thread.
Okay, so it's sort of by a logical operation in the application. Great.
Thank you.
All right.